Dear students, welcome to EPG Pathshala. As we all know, sun is the ultimate source of energy. The sun produces energy by means of nuclear fusion. Today, in this module, sun as an energy source, we are going to discuss on the structure as well as composition of sun, how the energy is produced, the reactions, the types of the reactions, and how much energy is produced in the sun. How this energy, the conversion, the mass energy conversion occurs inside the sun while reaching the earth. How long this energy in the sun will last. We will also see how the energy is transported within the sun and the energy, the solar radiation reaching the earth. We will also see how to calculate the energy reaching the earth from the sun. Once the energy reaches the sun, this has to be converted to different forms of renewable energy. And today we are looking into this renewable energy, the other forms like biomass energy by means of its photosynthesis, wind energy, OTEC, hydel energy, etc. All the base of these energy sources are sun. The sun is the largest object in our solar system. It has a radius of 6.9 multiplied by 10 to the power 8 meter, which is 10 to the power 9 times that of our earth. The mass of the sun is 2 into 10 to the power 30 kilogram, which is around 3 lakh earths. Let's see the structure of the sun. The interior of the sun is consisting of core, radiation zone, convection zone, then its atmosphere including the photosphere, chromosphere and corona. Core of the sun. It occupies 20 to 25% of the solar radius from the center. This center of the star plays the platform for fusion process. The energy emission in the sun, as we told, it is by the nuclear fusion. Here, the fusion of 4 hydrogen atom, that is proton, into one molecule of helium occurs at the core. The high energy production is the result of the high pressure and temperature that exists within the core. The pressure at core is equivalent to 250 billion atmosphere and temperature is 15.7 million Kelvin. So, the 99% of this energy production occurs in the core of the sun. Once this energy is produced, it is released away from the core by means of radiation in the radiation zone. This radiation zone extends out to about 0.7 solar radii from the core. In this zone, the radiation makes it hot and it helps in the transfer of heat from core in outward direction. The ionic forms of hydrogen and helium emitting photons in the zone travel a short distance before being reabsorbed by other ions. The temperature of approximately 7 million Kelvin at closer to the core is reduced to 2 million at the boundary with the convective zone. So, there is also a reduction in density with a range of 20 gram cubic centimeter closest to core to 0.2 gram per cubic centimeter at the upper boundary. So, at the convective zone, as the energy moves away from the core and passes through the radiation zone, it reaches the part of the star, the sun, where the energy continues its journey towards the surface as heat associated with thermal gradient. This zone is known as the convective zone. It has a lower temperature than the other zones and non-ionized heavier atoms are present. This lies in 2 kilometer to this zone lies in 2 lakh kilometer from the surface. The rising thermal cells carry the majority of the heat outward to sun's photosphere. Once these cells rise to just below the photospheric surface, their material cools, causing their density increase. This forces them to sink to the base of the convection zone again, where they pick up more heat and convective cycle continues. The atmosphere of sun, including the photosphere, chromosphere and corona. So, the surface of the star is known as photosphere. It has a thickness of around 500 kilometer. It emits light in the visible part of the electromagnetic spectrum. The star is engulfed in a stellar atmosphere which is known as chromosphere of thickness 2500 km. And it is a layer of hot gases surrounding the photosphere. Let's see the composition of photosphere. If you see the composition of atmosphere of the sun, except core, the other parts having almost similar composition. So it includes the major elements of hydrogen around 90% and helium around 8.89%. And the other minor elements are oxygen, carbon, neon, nitrogen, iron, magnesium, silicon and sulfur. The corona is sun's outer atmosphere. The sun's magnetic field rise through the convection zone and erupt through the photosphere into the chromosphere and corona. The eruptions lead to solar activity which include phenomena such as sunspots, flares, prominences and coronal mass ejections. Let's see the atmospheric condition of the sun. As we have already told, the surface pressure is very high. Like the core, the atmospheric pressure in the photosphere, that is at the top of the photosphere, is 0.868 million, is 0.868 millibar, and pressure at bottom of the photosphere is 125 millibar. The effective temperature at this photosphere is 5772 Kelvin. The temperature at top of photosphere is 44,000. The top of photosphere is 4400 Kelvin and at bottom of photosphere is 6600 Kelvin. While the temperature at top of chromosphere is around 30,000 Kelvin. Now let's see the nuclear fusion reaction in the sun. So the stellar nuclear reactions are responsible for the nuclear production, and we have seen that is mainly by the nuclear fusion. Here the hydrogen atoms combine together to form helium by this nuclear fusion, and the temperature inside the sun is greater than 10 to the power 7 Kelvin. So the sun releases energy at a mass energy conversion rate of 4.26 million metric tons per second, which produces the equivalent of 38,460 septillion watts per second. There are two types of reactions of this nuclear fusion. They are proton-proton chain reaction and the CNO, that is carbon nitrogen oxygen cycle reaction. And by this fusion reaction, the sun is able to emit 4 into 10 to the power 26 watts of power. Let's see the proton-proton chain reaction. It converts hydrogen atom to helium atom. So this reaction is more efficient in the lower mass stars like the sun. The reaction results in fusion of 4 proton into 1 alpha particle with the release of 2 positrons and 2 neutrinos, which further changes 2 of the protons into neutrons and energy. The CNO cycle. This reaction is important in the heavier stars and having temperature greater than 16 into 10 to the power 6 Kelvin. In this cycle, hydrogen is used to synthesize heavier elements. The heaviest elements are synthesized by fusion that occurs as a more massive star undergoes a violent supernova at the end of its life, and this process is known as supernova nucleosynthesis. The sun remains hot due to equilibrium maintained between nuclear reactions, chemical energy or gravitational energy, but it is inadequate to maintain luminosity for billions of years. The pressure balance, that is the gas pressure versus your gravity, and energy balance, that is production versus outflow, are both needed to regulate heat energy inside the sun. Let's see how much energy is produced in sun. The energy released during conversion of hydrogen to helium is mainly in the form of photons. So the energy released can be estimated from the mass difference. The mass of 4 proton is equal to 6.69048 multiplied by 10 to the power minus 27 kilogram. Mass of 1 helium atom is equal to 6.64648 multiplied by 10 to the power minus 27 kilogram. If you see the delta M, that is the mass difference, where the equation 1 minus equation 2, we will be having 0.04400 multiplied by 10 to the power minus 27 kilogram. and we know that E is equal to mc square. Applying this or substituting the m and c value, we will be getting 4 into 10 to the power minus 12 joule per reaction. If 10% of hydrogen is converted into helium for the sun, it will produce 10 to the power 44 joule of energy, which is sufficient to keep sun burning for 10 billion years. Let's see some calculations related with the energy production in sun. How much mass is converted to energy every second in the sun to supply energy to the earth? For that, let's start with the solar constant, which is equal to 1372 watt per meter square. And the radius of the earth is 6.4 into 10 to the power 6 meter. The distance, the earth to sun distance is 1.5 into 10 to the power 11 meter, and mass of the sun is 2 into 10 to the power 30 kilogram. So to get solar constant equal to the unit of mass, we have to do the solar constant divided by c square, that is E is equal to mc square. Applying that equation, we will get the value of solar constant in units of mass as 1.524 multiplied by 10 to the power 14 kilogram per second. So total energy falling on the earth is solar constant times the projected area of the earth from the sun. Then that value will be equal to area of the earth multiplied by solar constant. Applying that values, we will be having 2 kilogram per second. That value, that is 2 kilogram per second, is the mass converted every second to supply light incident on earth. Let's calculate how much metric tons of hydrogen are converted to helium to supply this energy. For this, the mass of hydrogen nuclei or the proton is 1.67262 multiplied by 10 to the power minus 27 kilogram. And the distance, the earth sun distance is 1.5 into 10 to the power 11 meter, and mass of helium is 6.64648 multiplied by 10 to the power minus 27 kilogram. And the mass difference between 4 protons and 1 helium nucleus, we have already calculated it as 0.044 into 10 to the power minus 27 kilogram. The ratio of hydrogen burned to converted mass is equal to 6.69048, that is the mass of the 4 protons divided by the mass difference, that is 0.044, will give you 150, or it is equal to 0.7% of rest energy or mass of the original hydrogen is converted to helium. So the total mass burn rate of the sun is equal to 150 multiplied by 4.2 into 10 to the power 9 kilogram per second, which is equal to 6.3 into 10 to the power 11 kilogram per second, that is 630 million. So 630 million metric tons of hydrogen are converted to helium to supply the energy. Let's calculate how long this sun will continue to produce this energy. We are ignoring, for this, assume that the other processes and emissions from the sun are ignored. So let's find out the lifetime of the sun is equal to the mass of the sun divided by the burn rate, which is equal to the mass of the sun is 2 into 10 to the power 30 kilogram, and the burn rate we have already calculated 6.3 into 10 to the power 11 kilogram per second, and we will be getting around 10 to the power 11 year. The sun converts only 10% of its hydrogen mass to helium. So the above estimate is high by a factor of 10. So deducting that value, we can get the mean lifetime of sun as 10 to the power 10 year. Now the energy is produced inside the sun, mainly inside the core. So it has to be transported outside. Let's see what are the mechanisms of this transport. So we know that the energy transport is mainly by means of convection, convection and radiation. Convection, which is a transfer of energy by movement of heated substance. Convection, where the transfer of energy as a result of temperature difference between substances that are in contact. Radiation, where the propagation of electromagnetic waves from one location to another. In sun, we can see that at the core, the energy transport mechanism is convective, while at radiation zone, it is radiative, and convective zone, it is convective. So the mechanisms of the energy transport in sun are convection and radiation. The sunlight that reaches the earth depends on the revolution of the earth around the sun. The orbit of the earth around the sun lies in a geometrical plane that is known as orbital plane. The plane of orbit that intersects the sun is known as ecliptic plane. The line of intersection between the orbital plane and the ecliptic plane is known as line of nodes. The planetary orbits, including the Earth's orbit, lies in the ecliptic plane. Now, let's see the distance between the sun and the earth. Normally, the distance between sun and earth is measured in AU, that is astronomical unit, and this is equal to, or 1 astronomic unit is the distance travelled in 8.31 minutes at the speed of light. The mean distance of sun from earth is 149.6 into 10 to the power 6 kilometer with a minimum of 147.1 multiplied by 10 to the power 6 kilometer and maximum of 152.1 multiplied by 10 to the power 6 kilometer when the earth is away from the sun during its revolution. The flux of solar radiation incident on a surface placed at the edge of the earth's atmosphere depends on the time of the day and the year and the geographical location of the surface. Some incident solar radiation is reflected by the earth's atmosphere. The fraction of solar radiation that is reflected back into space by the earth atmosphere system is called albedo. The solar radiation is absorbed or reflected by clouds is around 20% as per the earth's energy budget, and atmospheric particle is around 6% and reflection by the earth's surface is 4%. So, around 30% is absorbed or reflected. That is why the albedo of earth is around 30%, and these are preventing the radiation reaching the earth's surface. The solar flux that enters the atmosphere is reduced by the albedo, as we have already seen. So, the solar radiation undergoes absorption, reflection or scattering by air, water vapor, dust particles and aerosols while travelling to earth. The solar radiation are of two types. One is that reaches directly to earth is the direct solar radiation, and that reaches after scattering is known as diffuse radiation. What is solar constant? The amount of radiation from the sun that reaches the earth's atmosphere is called solar constant. The quantity of solar energy at normal incidence outside the atmosphere at the mean sun-earth distance is known as solar constant. It is expressed as watt per meter square. Normally, the value is 1372 watt per square meter. This, though the name is solar constant, it is not a constant value. This constant varies with time because the earth follows an elliptical orbit around the sun and the axis of rotation of the earth is inclined relative to the plane of the earth's orbit. Distances between points on the surface of the earth and the sun vary throughout the year. Because of all these, the solar constant varies. This figure shows the solar radiation spectrum for the direct light at both the top of the earth's atmosphere and at the sea level. We can see the spectral irradiance versus the wavelength of the radiation. What is its irradiance at the atmosphere and at the sea level? Now, let us calculate how much solar energy is received on earth. For this, we can solve this by an equation. Solar power incident on surface multiplied by the time. So, for example, the solar power incident on surface averages 400 watt per meter square for 12 hours. How much energy is received? For this, 400 is the solar power incident on surface and 12 hour is the time. So, just multiply those. 400 watt per meter square multiplied by 12 hours will give you 4800, that is 4800 watt hour per meter square, which is equal to 4.8 kilowatt hour per meter square. That is the energy received by the earth from the sun. Another example, the amount of solar energy collected on a surface of earth over 8 hours is 4 kilowatt per meter square. What is the average solar power received over this period? For this, 4 kilowatt hour per meter square divided by the time, that is 8 hours, will give you the average solar power received over this period, which is equal to 500 watt per meter square. So to conclude, we have seen in this module the structure of the sun. The interior of the sun consists of core, radiative zone and the convective zone, where the core is the main part where the nuclear fusion occurs, the 99% of the energy is produced in the sun. And the atmosphere of the sun consists of photosphere, chromosphere and the corona. And we have seen the composition of sun as the main components are the hydrogen and helium, with some minor elements such as nitrogen, oxygen, iron, etc. We have seen the reactions which occurred inside the sun at the higher pressure of 250 billion atmosphere and high temperature of 15 million Kelvin. Under this high pressure and temperature, the reactions of nuclear fusion occurs, and we have seen the two main types of nuclear fusions are the proton-proton chain reactions and the CNO cycle reaction. And in sun, the reaction is the proton-proton reaction, where the 4 protons combine to form the one molecule of helium. Once the energy is produced inside the sun, the amount we have calculated how much energy or the mass is converted to produce the energy. It was around 2 kilogram per second, and the 630 million metric tons of hydrogen is converted to helium. And this is enough, this burn rate is enough to keep the sun hot for 10 billion years. Then we have seen how the energy is transported from the core to other zones. That is mainly by the convection and the radiation process. And from the sun, the energy is reaching the earth, but the radiation is not reaching because of the absorption, reflection and scattering processes. And we have also seen the role of albedo in this reduction. Now, we have also seen the solar radiation, the Earth's energy budget, as well as the solar radiation spectrum on the Earth. We have seen why the solar constant varies with time, and also we have calculated the solar energy received on the Earth. We can calculate this value by multiplying the power, the solar radiation incident on the area multiplied by the time. Thank you.